All right, chapter 12. So chapter 11 was about rotational motion, things moving in a circle. Everything we had done prior to that was things moving in a straight line. But can things not move in a circle and a straight line? Like say, a tire? They probably can. Okay, so that's what chapter 12 is about. It's really about rolling motion. And then we have a couple subsets, a little more on torque and a little bit on angular momentum, which we have not yet talked about momentum in the rotational world, so we'll mention that too. But I'm going to save this topic for next class. Anyway, rolling motion. Refer to this picture. What is the distance, according to this picture, traveled by the wheel's center of mass? S. So our displacement would simply be S, according to this picture. And if we divide that by time, or took the derivative with respect to time, that would be the velocity of the center of mass. Okay, so things we remember, we want to talk about arc length, or the angle that's swept out is arc length divided by radius, which gives us this equation we already knew. If we take the derivative of both sides with respect to time, we basically end up with a formula we also already knew, the marching band equation, but again, a way of coming up with the velocity of the center of mass given the angular velocity and the radius. Now, next question. Imagining this rolling. So we're rolling. Which of little point rubber at the bottom of the tire or the top of the tire would be moving faster as far as a tangential velocity at any given moment? Or would it have to be the same?
With the direction.
Imagine the combination of these pictures. Purely rotational motion, okay, like this. If I was talking about purely rotational motion, the tangential velocity of the top and bottom would be the same, albeit direction. Same radius. If I'm talking about linear motion, we're just like doing this. It also be the same, but in the same direction. So if you kind of think of the overlap of these two, the top actually would be going twice as fast as the center of mass, and a point at the bottom would actually not be moving for that instant, which is kind of interesting to think about. Now this is a constant velocity scenario as far as the center of mass goes. If you are accelerating, speeding up in your car, slowing down, there would definitely be motion of this point, and that's where we'd have the friction. But in a purely constant velocity scenario, we actually say that point is not moving at the bottom. And there's a good picture of this in the book. If you go to page 270, that kind of shows this. Page 270. First, just look at the picture at the top left, the bicycle wheel that's rolling along the ground. Where is it the least blurry? The bottom. Okay, where this is not moving at that point. Now the top, especially if you're trying to look at the little spokes, they become more and more blurry, and it's the most blurry at the top, where that would be going twice as fast as the center of mass, and the bottom, 0. All right, so we're going to do checkpoint number 1 right there. Let's also remember our marching band equation, which we just wrote down as well. All right, checkpoint number 1 says the rear wheel on a clown's bicycle has twice the radius of the front wheel. A, is the linear speed at the very top of the rear wheel Greater than, less than, or the same as the front wheel? Tough question. What do you think? Okay, let me ask you a different question first. How would the velocity of the center of mass compare, just right smack in the middle, of the rear wheel versus the front wheel? They should be the same. Otherwise, your bicycle is coming apart. Okay, you can't have one part going faster than the other part. So they should be the same. So at least we know the velocity of the center of mass should be the same for the front wheel and the rear wheel. But it says, what about a point at the very top of the rear wheel? They would have to be the same, because regardless of what your radius is here, the very top is going to be double the center of mass. But we did have to figure out the center of mass would be the same. So they'd be the same. But what about the angular speed of the rear wheel versus the front wheel? With the angular speed, so now radius is involved. Would the angular speed be greater than, less than, or the same as the front wheel?
Which one was bigger again?
The rear wheel is bigger.
So that has a lower range.
So good, because it's got a bigger R, so it's got to have a smaller omega to keep the same velocity, or center mass velocity the same. Okay. And I'm in the pen. Okay. I'm stopping at angular momentum, yes. Okay, a uniform, solid, cylindrical disk whose mass m is 1.4 kilograms and whose radius is 8.5 centimeters rolls, okay, so now we know we're in chapter 12, across a horizontal table at a speed v of 15 centimeters per second. Okay, A. What is the speed of the top of the rolling disk? It's got to be 30 in centimeters per second. Okay, that's just double. What is the angular speed of the rolling disk? How did we tie in angular speed? What's the equation?
The center of mass velocity and angular speed.
Very good. So this was 15, although, well, we leave it 15. They're both in centimeters, that's fine. 15 equals omega times 8.5. 1.8?
I'm just guessing.
Close, 1.76. And that would be radians per second. Okay, and then C. What is the kinetic energy of the rolling disk? What would I need to know there?
Inertia.
I would need to know the moment of inertia. So what's that formula?
That's 1/2 omega.
Okay. Is it just rolling? That was not the question. Is it just spinning in place? Like everything we did in chapter 11? No. This would have been fine for chapter 11. But it not only has rotational kinetic energy, but it also has, yeah, linear kinetic energy. So we can't forget that part too. So we also have to plug in our old favorite, 1/2 mv squared. And remember I for a cylinder? Yeah, there's usually mr squared. Is there a fraction this one or not?
Or second.
Central axis,
Yep.
1/2 mr squared.
Good. That part, okay, so I is 1/2 mr squared. All right, so hopefully we have all of this and fit it in this line. Do we have the m? Yes, 1.4. Let's make sure our radius this time, let's put everything in meters. We're all in standard metric units, so change that to 0.085. So that's the I. Then the omega was from over here. And if we can see if we have two of the same answer. All right, thank you. So not that that's very difficult to remember that one extra part, but don't forget that if something is rolling, it's got rotational and linear kinetic energy. Because if we're doing conservation of energy, we forget part of that. That will, of course, mess us up. Okay. Well, this probably should have come before that slide, but because I want you guys to finish that lab.
Finish slash start.
Finish.
There's start.
You guys should be 2/3 done. They're going to steal your data.
Should be 2/3.
Okay, we're good? Great. I guess I kind of already mentioned this one. Friction while rolling. According to this picture, friction does not affect this rolling wheel. Why? Because it doesn't.
It wouldn't slow it down. Friction would be going that way. Friction would be going the same way. Didn't you say it wasn't moving at all?
Right. Friction opposes motion, which to have this scenario in real life would be fairly unrealistic. As far as moving tires, they're always slowing down, speeding up with air resistance and just stepping on the gas pedal. But friction opposes motion. So if this point is not sliding, it's still right there, then friction would not affect this problem at all, which is at least helpful for our problems. When will friction affect rolling motion? When it is either speeding up or slowing down. But I don't believe they bring in friction at all in this chapter, unless it's just a conceptual question. Like number 2 here. All right, 274. And this is going to Connor. Okay, disks A and B are identical and roll across a floor with equal speeds. Then disk A rolls up an incline, reaching a maximum height h, and disk B moves up an incline that is identical, except that it's frictionless. Is the maximum height reached by disk B greater than, less than, or equal to h?
Well, no. Friction aids it.
And now I forgot which one had friction.
The equal gravity with that foot.
Disc A has friction.
Disc A. Okay, so A is a friction.
So basically, the car's going up the hill, and then another car's going up the same hill with ice.
Okay. Okay, I got it. B is frictionless. Okay, so what did you just say about friction? Is friction helping it go up the incline or not? It does. Because, okay, so it's going up the incline. You know, you imagine a point of contact of the wheel going that way. And of course, this is a case where it would want to speed up or slow down. Of course, slow down if it's going up an incline. So friction would be present. But if this point is going like this way, we're going up the incline, friction opposes motion, would actually push it up. From a conservation of energy standpoint, how can that be? Because they start with the same energy, right? They have the same speed, both rotating. They start with the same kinetic energy, so shouldn't they both end with the same potential energy? No. Okay, good, because we of course have friction doing some work. But here's the one thing that we don't necessarily think is happening, but would be happening. In the frictionless case, would it ever stop spinning? No. It would reach some maximum height, but it would still just be doing this. So if you're thinking about your conservation of energy, in case B's scenario where it's frictionless, some of its energy is now potential, but some of it's still kinetic because it's still rotating. So with the friction case, more of that energy can turn into potential. Interesting question. But it is important to realize in the frictionless case, the spinning one would not stop spinning. Okay, let's do this one and be done here. All right, so we have the hoop and the disc. And we kind of did this in class. They roll from rest down an incline whose length is 2.1 meters, angle 34 degrees. How fast is each object moving at the bottom of the ramp? And first of all, hopefully my picture's not misleading. If they have the same mass and same radius, which one has the greater moment of inertia? What did you say? The hoop. Because same mass, but all that mass is more spread out. Some of this mass is closer to the rotation point. So the hoop's going to have the greater rotational inertia, and therefore should not win the race. But let's see if we can answer this. How fast is each moving at the bottom of the ramp? Okay, this is going to be a big conservation of energy question. And I'm going to need you guys with the numbers. So in this case, we're just saying the initial potential up here should turn into all kinetic at the bottom. But of course, that kinetic is two types of kinetic, rotational and linear. So we should start off with the same potential energy, which would be, what is our potential energy formula? MGH. And they didn't give us the height, did they? They gave us L. That's annoying. All right, what was L? All right, so we got to do just a little trig for a second. We got the hypotenuse, and we got our angle. So opposite side is going to be What is it? 1.17 is going to be sine. Sine of 34 equals h over L.
Might be a non-mode.
Oh, we should be in degrees. 1.17 sounded reasonable, is that right? Okay. All right, and what is the mass? Either way, this should have been the same mass.
7.2.
Okay, so that's just potential energy. And I guess let's do, well, just tell me what that is, because then we can at least steal this number for the, when we do the disk. Okay, so the original energy is 82.6. That should be conserved. Okay, so let's do the hoop first. No particular reason. Does the hoop? I think the hoop is just mr squared. Can someone check that for me? And I think that's the 1/2. Mr squared. All right, so anyway, right now in our formula we've got the rotational part, and the linear part. And we're going to do the hoop first. Half times 7.2. What is the radius of either? 0.11 squared. And then omega. Do I have omega? I don't know anything about the angular speed at the bottom. What am I even trying to find at the bottom? The speed? Okay, well, often, the way we associate that with alpha the same way is what formula relates omega and v? It's the first formula at the beginning of this chapter. Our marching band formula works for alpha or... Yeah, so don't forget that. Much like in torque, often we'll plug in, A equals alpha R. Marching band equation is very helpful. So I want to get rid of omega, and I'm going to have to plug in instead V over R. So I will have two unknowns here, but that's okay. And that is all squared. All right, plus 1/2 times 7.2, and then just v squared. And I'll try to save you some pain here. Oh. Let's just say we got that. That is the speed of the hoop at the bottom where potential energy is 0. Now, out of this whole equation, what's really the only thing we need to change for the disk? The disk had the same mass, same radius, the moment of inertia. So all I would have to do for the disk put a 1/2, in here. That's it. Otherwise, the same exact thing. So again, I will try to save you that trouble. Did the one that I expected to be faster end up being faster? Yes. The hoop was slower and it would have taken more time to get there.